Welcome back to QHSE Talks. When you think about keeping people alive for a living, there's this assumption that it's all about rigid rules. You just memorize a checklist, you throw on a hard hat, and boom, you are safe. But the reality is occupational safety isn't a checklist at all. It is a massive, multidimensional puzzle.
It really is.
And today we are speaking directly to you, the listener. Whether you are, barricaded in your office, staring down the grueling associate safety professional exam, the ASP, or maybe you are a professional whose actual day job is making sure workers go home to their families, this session of QHSE Talks is custom built for you.
Yeah, and it is entirely a puzzle. And the stakes of this particular puzzle, they couldn't be higher. You aren't just trying to figure out what went wrong after an accident, right?
Yeah.
You're tasked with calculating the exact probability of something breaking in the future, and then engineering a reality where that failure literally never happens.
Yeah, and to do that, we've taken a massive stack of your sources. We've got the BCSP exam blueprints, the OSHA handbooks, the Bowen EHS study materials, and just a ton of practice questions.
A lot of reading.
So much reading. We have synthesized all of it for this session. Our mission today is to shortcut your path to being well-informed on Domain 2, Topic 8, Part B, which is the absolute gauntlet of working at heights, and Domain 1, Topic 7, which gets into the terrifying math of fall protection calculations.
Which is such an essential skill because, passing the ASP exam means getting the math right on paper.
Yeah.
But performing your duty as a safety professional means, understanding the physical reality behind that math so a worker actually survives their shift.
Okay, let's unpack this from the very beginning, because before we even let a worker climb a ladder, we need to establish who is actually qualified to make these life and death calls. What actually qualifies someone to sit for the ASP exam in the first place? I assume it's more than just a weekend seminar.
Oh, considerably more, yeah. The Board of Certified Safety Professionals, the BCSP, they set a very strict baseline. First, you need an academic foundation.
Right.
That means at least a bachelor's degree in literally any field, or an associate degree specifically focused on safety, health, or the environment. But the degree is just the entry ticket. You also must have at least 1 year of professional safety experience.
Professional safety experience. That sounds like a phrase a lawyer wrote.
It does?
Does that mean running a fire drill once a semester counts? Because I feel like there's a massive gap between checking a fire extinguisher tag and, designing a complex fall arrest system.
And that gap is exactly what the BCSP evaluates. They define this through the density of your responsibility. Your daily duties must consist of at least 50% professional level safety functions.
Wait, 50% of your entire time?
Yes. And if you're working part-time, they quantify that as at least 900 hours a year.
Wow.
Which is roughly 75 hours a month, purely dedicated to safety at a professional level.
I want to push back on that term, though, professional level. What does that actually look like on a Tuesday morning at a job site? I can guess what it isn't. It isn't just handing out safety glasses or ordering steel-toed boots from a catalog.
Exactly. The key concept here is professional charge.
Yeah.
The BCSP is looking for reliance. Is the employer, are the employees, or are the clients actively relying on your specific ability to identify, evaluate, and control hazards?
Ah, okay.
You have to demonstrate that you are the one assessing risks quantitatively, investigating the root causes of incidents, and designing administrative and engineering controls. You are the architect of the safety system, not just the hall monitor enforcing it.
So you are the person the company relies on to anticipate disasters before they occur. Which actually brings up a fascinating philosophical question from the Bowen EHS materials. You've got all these blueprints, you're calculating structural loads, you're designing training programs, and you're auditing compliance. Based on the source text, is the safety professional's job primarily an engineering problem, an educational one, or an enforcement one?
What's really fascinating here is the answer the exam materials point you toward,
Right.
because it completely defies expectations. You'd look at the math we're about to do and assume, it's an engineering problem.
Right.
But the correct conceptual framework is that safety management is primarily a motivational problem.
I would have absolutely guessed engineering. Why motivational? If you engineer a guardrail that can stop a heavy truck, why does motivation matter?
Because human beings are remarkably adept at bypassing engineering if they aren't motivated to use it.
That is so true.
If we connect this to the bigger picture, you can engineer the absolute perfect full body harness. You can calculate the fall clearance down to the millimeter. But if the safety culture on that site does not motivate the worker to actually put the harness on, adjust the leg straps correctly, and clip the lanyard into the anchor point when they're, tired and running behind schedule, the entire multi-million-dollar safety system fails.
Ah, I see. Education tells them how the carabiner works. Enforcement threatens to fire them if they don't use it, but motivation is what ensures they actually clip in when nobody is watching them.
Precisely. Behavioral psychology is the invisible foundation of the safety profession. You have to communicate the reality of the dangers so clearly and build a culture so supportive that workers are intrinsically motivated to protect themselves.
And to build that intrinsic motivation, you have to help them understand the sheer brutality of the physics they're up against. Which brings us to the single most fatal hazard on any construction site heights. Let's define the parameters. What exactly constitutes working at height according to the regulations?
The ISO 45001 implementation guide defines it very broadly. Working at height is working in any place where a person could be injured if they fell from one level to another.
So that could be a 3-story roof, but it could also be like a loading dock. It includes falling into things too, right? Like a grain silo or a chemical vat.
Yes, entrapment hazards absolutely count. But for the ASP exam, you have to understand OSHA's regulatory split because the rules change depending on the industry. OSHA sets the threshold for requiring fall protection at 4 feet for general industry. But for the construction industry, it is 6 feet.
Okay, I have to ask, why the difference? Did gravity suddenly get 33% weaker on construction sites?
Right.
Why does a warehouse worker need a harness at 4 feet, but a framer is fine until 6 feet?
It's a great question, and it highlights the difference between pure physics and regulatory compromise. Gravity is identical. The difference stems from the historical evolution of the standards, industry lobbying, and the practical realities of the work environment.
Okay.
Construction is inherently dynamic. The environment changes hourly. Imposing a 4-foot rule in construction was deemed overly burdensome for tasks like foundation work or low-level framing. General industry is static. A 4-foot platform in a factory isn't moving, so guarding it permanently is much easier. But of course, physics doesn't care about OSHA's compromises.
Here's where it gets really interesting for you, the listener. Let's look at Domain 1, Topic 7, which covers the terrifying math of a fall. A body in free fall accelerates due to gravity at 32 feet per second squared, or 9.8 meters per second squared. I think people hear acceleration and picture a sports car. They don't intuitively grasp what that means for a human body.
To grasp it, we have to look at the intersection of that unrelenting gravitational pull and human neurology. We really need to talk about human reaction time.
Right, because if I trip over an extension cord right now, my hands shoot out to catch me. It feels instantaneous. So if a worker slips off a leading edge, instinct says they'll just grab a nearby piece of rebar and catch themselves. If I had to guess the math, I'd say it takes a human, a tenth of a second to react?
Your guess is completely normal, but biologically incorrect. The human nervous system is a physical network of electrical impulses traveling through nerves, and that travel takes time. The data shows it takes approximately 1/3 of a second, about 0.33 seconds, just for a person to cognitively realize they're falling.
Wait, just to realize it?
Yes. Your foot slips. The fluid in your inner ear, your vestibular system, shifts. That signal travels to your brain. Your brain processes the unexpected loss of equilibrium, and the conscious realization of "I am falling" occurs. That entire process eats up 1/3 of a second.
And during that 1/3 of a second, my hands are still at my sides. I haven't moved to save myself yet.
Exactly. Then phase 2 begins. The brain has to formulate a physical response and send electrical signals down your spinal cord to your motor neurons. Your muscles have to contract to throw your arms out or shift your weight. That physical reaction takes another 1/3 of a second.
So we are looking at roughly 2/3 of a second of total neurological lag time before the human body mounts any sort of physical defense.
Correct. Now let's apply the acceleration of gravity, 32 feet per second squared, to that 0.6 seconds of human lag.
This reminds me of old cartoons. You know, Wile E. Coyote runs off a cliff, stops in midair, looks down, holds up a little sign that says, "Uh-oh," and then plummets. We have this psychological illusion that we hang in the air while our brain catches up. But the mechanism of gravity doesn't pause for nerve conduction velocity, does it?
It doesn't pause at all. This is the mechanism you have to understand. While the worker's nervous system is taking 2/3 of a second to process the slip and tell the hands to grab a beam, gravity has already taken over. By the time that worker's hands physically begin to close around where they thought the beam was, their body has already plummeted downward at least 21 feet.
21 feet. You've fallen 2 stories before your brain even gets your hands into position.
Yes. You haven't grabbed the beam. The beam is 21 feet above you. In most industrial scenarios, you have already impacted the ground. This raises an incredibly important question for the safety professional. When designing a system to protect a worker at heights, can you ever rely on a worker's reflexes to act as a safeguard?
The answer has to be no. The biology simply won't allow it.
An absolute, unequivocal no. And that translates directly into exam strategy and site design. You cannot design a system that requires active split-second deployment by the user. You can't hand a worker a trailing rope and say, if you slip, pull this brake immediately.
Right.
The system must operate independently of human reflexes. It must be passive, like a guardrail, or automatic, like a self-retracting lifeline that locks via centrifugal force.
The system has to save them because they physically cannot save themselves. That perfectly sets up the hierarchy of controls. If we know human biology fails at heights, how do we protect them? Let's imagine a practice question. What is the absolute best way to protect a worker tasked with inspecting the flashing on a 3-story roof?
If you follow the hierarchy of controls, the apex, the absolute best method is always elimination. You completely eliminate the need for the worker to access the elevated area entirely.
Which means what? We just don't inspect the roof.
No, the work still has to be done, but you change the method. You send up a drone equipped with a 4K camera to inspect the flashing while the worker stands safely on the ground. Or, if you're constructing a steel tower, you assemble the large sections on the ground and use a crane to hoist the completed module into place, rather than having workers bolt it together piece by piece 80 feet in the air.
Got it.
If you eliminate the height, you eliminate the fall.
But practically speaking, elimination is rare. Eventually, a human roofer has to go up there to nail down the shingles. An HVAC tech has to service the rooftop unit. When you cannot eliminate the hazard, and maybe it's too early in construction to have permanent engineering controls like parapet walls, we step down the hierarchy. We rely on administrative controls. Let's look at the cornerstone of OSHA's administrative rules, the competent person.
The term competent person is heavily scrutinized on the exam. It is a very specific legal designation. It is not just the foreman, and it is not just the person who has been there the longest. A competent person is someone who is capable of identifying existing and predictable hazards in the surroundings or working conditions.
Predictable hazards, meaning they don't just see the hole in the floor, they see that a forklift path runs right next to the hole in the floor.
Exactly. And the second, most vital half of that definition, they have explicit authorization from the employer to take prompt corrective measures to eliminate those hazards.
They have the absolute authority to stop the job.
If they cannot stop the job, they are not a competent person under the standard. Their role is massive. If you are erecting scaffolding, the competent person designs the plan, ensures the base is sound, and inspects it daily. If a storm is rolling in, it is the competent person's legal duty to monitor the wind speed and unilaterally decide if the workers need to evacuate the scaffold.
Let's look at a very specific and highly controversial administrative control that relies on a competent person. Let's say a crew is pouring a concrete deck on a high-rise. They are working right on the leading edge. You can't put a physical guardrail up because the edge is actively being formed. In this scenario, OSHA allows a safety monitoring system. How does that work?
A safety monitoring system relies on a designated competent person whose sole exclusive job is to act as the eyes for the workers. They monitor the crew and orally warn them if they are getting too close to the fall hazard or acting unsafely. But the rules governing this monitor are incredibly strict, and you will see them on the exam.
I can see the exam questions now trying to trick you. Let's break down the rules.
First, the monitor must be positioned on the same walking or working surface as the employees being monitored. They cannot be on the ground looking up with binoculars. Second, they must be within visual sighting distance of the employees at all times. Third, they must be close enough to communicate orally. Their warning has to be heard clearly over the ambient noise of concrete vibrators and diesel engines.
And the fourth rule, I feel like this is the one that gets companies cited the most.
The monitor must have absolutely zero other responsibilities that could take their attention away from the monitoring function.
Let me push back. What if they're just reviewing the blueprints for the pour while they stand there, or checking their phone for a quick text from the superintendent?
The moment their eyes drop to a blueprint or a phone screen, the safety monitoring system ceases to exist. Think back to the math we just did. If the monitor glances at a text message for exactly 2 seconds and a worker walking backward with a concrete hose trips...
2 seconds. A body accelerating at 32 feet per second squared. In 2 seconds, they've fallen over 60 feet.
Exactly. The human cost of a momentary distraction is a fatality. This is the inherent glaring flaw in administrative controls. They rely on sustained human vigilance. Psychologically, humans are terrible at continuous vigilance tasks. We suffer from vigilance decrement. Our attention naturally wanders when staring at a static scene.
Which is why administrative controls are lower on the hierarchy. When human attention fails, we need physical barriers that don't blink. We need engineering controls. Let's start with the platforms that put workers in the sky scaffolding. What are the engineering fundamentals a safety professional must know?
Let's start at the foundation. The base support must be rigid, stable, and level. You cannot build a scaffold on shifting mud, loose bricks, or uneven debris. But the critical exam focus is the load-bearing math. A standard scaffold and its components must be capable of supporting, without failure, its own weight and at least 4 times the maximum intended load.
4 times. So if the workers, their tools, and the pallet of bricks weigh 1,000 pounds, the scaffold must be engineered to hold 4,000 pounds.
Yes, that's for ground-supported scaffold. But the rules change drastically for a suspension scaffold.
A suspension scaffold being like the platforms window washers use, hanging from the roof by cables.
Correct. For a suspension scaffold, the rigging, the ropes, the wires, the roof irons must be capable of supporting at least 6 times the maximum intended load.
Okay, let's unpack this. Why the jump from a 4x safety factor to a 6x safety factor? It's the same workers and the same tools.
Because the physics of the load changes from static to highly dynamic. A scaffold built from the ground up is relatively rigid. The forces are pushing straight down into the earth. But a suspension scaffold hangs in the air. When a worker walks from one side to the other, the platform tilts. If a gust of wind hits it, it swings.
It's acting like a pendulum.
Exactly. And when that swinging platform reaches the end of its arc and changes direction, or when the hoisting motor starts and stops abruptly, it creates immense dynamic shock loads on the wire ropes. It's the difference between gently standing on a bathroom scale versus jumping onto it. Your mass didn't change, but the dynamic force spikes. The engineering must account for those spikes, hence the 6 times requirement.
That makes perfect sense. So we have a platform that won't collapse. But what if the worker has to reach beyond the guardrail, or what if there isn't a guardrail yet? We shift to personal fall arrest systems, the PFAS, the classic full-body harness and lanyard. Let's talk about the anchor point, because the harness is useless if what it's attached to rips out of the wall.
The anchor point is the absolute linchpin of the system. OSHA mandates that an anchor point used for a personal fall arrest system must be capable of supporting at least 5,000 pounds per employee attached. Or it must be designed and installed as part of a complete system with a safety factor of at least 2 under the supervision of a qualified person.
5,000 pounds of force per worker. The OSHA manual has a brilliant, vivid analogy for this that I just love. They tell trainers to ask workers, would you hang your new pickup truck from this anchor point?
It is the perfect visual translation of the math. A standard Ford F-150 weighs roughly 4,500 to 5,000 pounds. If you look at a piece of unistrut, or a decorative balcony railing, or a PVC pipe, and you cannot confidently visualize hoisting a pickup truck into the air by that object without it snapping, do not let a worker tie their life to it.
It instantly shifts the worker's perspective. So we have a truck-rated anchor point, we have a worker in a harness, we have a lanyard connecting them. This brings us to what I consider the most critical life-saving calculation on the entire ASP exam, calculating total fall clearance.
This is where safety professionals really prove their worth. Spotting a clearance failure on a blueprint before it happens in reality is a mandatory skill. Let's walk through a classic scenario you will definitely see on the exam and in the field.
Okay, listener, I want you to actively visualize this geometry. Here is the scenario. You have an employee who is exactly 6 feet tall. They are working on the second-story deck of a building under construction. The height from the concrete deck they are standing on to the ground below is exactly 12 feet. They are wearing a full-body harness. The only anchor point available is at their feet, right at the deck level. They tie off to it using a standard 6-foot lanyard. That lanyard has a shock-absorbing pack built into it that deploys to 3.5 feet. The question is, are they safe? If they fall off the edge, does the system prevent them from hitting the ground?
Let's methodically trace the physics of this fall. We have to calculate the total fall distance required to completely arrest the worker's momentum, and then compare that number to the available clearance, which is 12 feet.
Okay, I'll take a swing at the math. If they fall off the edge, the first thing that happens is they drop the length of the lanyard before it goes taut. That's 6 feet.
Correct. 6 feet of pure free fall.
At 6 feet, they hit the end of the rope. That sudden jolt triggers the shock absorber. The pack rips open, decelerating their fall so their internal organs don't rupture from the sudden stop. The problem states the shock absorber adds 3.5 feet of length as it tears open. So, 6 feet of lanyard plus 3.5 feet of shock deployment equals 9.5 feet of total drop. The deck is 12 feet high. 12 minus 9.5 leaves me with 2.5 feet of air between the worker and the ground. They're safe.
And if you select that answer on the exam, you fail the question. And if you approve that setup on a site, the worker dies.
Wait, what did I miss? The gear measures 9.5 feet.
You miss the human being inside the gear. You calculated the length of the hardware, but the hardware attaches to a soft, stretchy human body. First, consider the D-ring on the back of the harness. When a worker falls and the lanyard snaps taut, the heavy nylon straps of the harness stretch upward, and the D-ring slides up slightly toward the back of the head. We usually calculate about 1 foot of harness stretch.
Okay, so that puts us at 10.5 feet. Still got 1.5 feet of clearance.
Now, where is that D-ring located relative to the worker's body? It's between their shoulder blades. When they are hanging vertically in midair, you have to account for the distance from that D-ring down to the soles of their boots. If the worker is 6 feet tall, the distance from their upper back to their feet is roughly 4.5 to 5 feet.
Oh, wow. So the bottom of the system isn't the end of the lanyard. The bottom of the system is the worker's feet dangling 5 feet below the lanyard.
Exactly. Let's recalculate the geometry. 6 feet of lanyard freefall, plus 3.5 feet of shock absorber deceleration, plus 1 foot of harness stretch, plus 5 feet of human body hanging below the attachment point. That totals 15.5 feet.
And the deck is only 12 feet high.
The worker's feet hit the concrete ground before the shock absorber has even fully deployed. They impact with bone-shattering force. And we haven't even added the mandatory regulatory safety factor. You always add an extra 2 to 3 feet of clearance buffer for variations in equipment and installation. Realistically, tying off at your feet with a 6-foot lanyard requires at least 17.5 to 18.5 feet of clear space below you.
That is genuinely terrifying. The worker puts on the harness, inspects the lanyard, ties off to a 5,000-pound anchor, and feels completely secure. But the invisible geometry guarantees they will hit the ground. So, as a safety professional, how do you fix this system?
You have to change the geometry to eliminate the free fall. First, raise the anchor point. If you anchor overhead rather than at foot level, you eliminate the initial 6-foot drop. Alternatively, eliminate the 6-foot lanyard entirely and use a self-retracting lifeline, an SRO. It operates like a car seatbelt. It keeps tension on the line and locks up within inches of a fall occurring, drastically reducing the required clearance.
And let's assume a worker is using a proper system with plenty of clearance, and they fall. The shock absorber rips open, deploys fully, and saves their life. They are pulled back up safely. What is the procedure for that piece of equipment?
You take a pair of heavy shears, you cut the lanyard into pieces, you throw it in the dumpster. Equipment that has been subjected to a shock load during a fall arrest must be immediately removed from service. The internal stitching designed to absorb energy has been destroyed. The nylon fibers have been stressed beyond their elastic limit. It is structurally compromised and can never be used again.
Okay, we've spent a lot of time on leading edges and high-rise scaffolds. But let's bring it back to earth, to the everyday hazards, the tools you can buy at a local hardware store. Let's talk about ladders.
Ladders are incredibly dangerous precisely because of their familiarity. People are terrified of walking on an iron beam 50 feet up, so they hyper-focus on safety. But everyone has used a stepladder to change a light bulb in their kitchen, so they completely disrespect the hazard on a job site.
Let's run through a practical scenario from the source materials. You are an ASP walking the site. You see an employee who weighs 156 pounds. They are wearing a leather tool pouch that weighs 15 pounds. They are standing on an A-frame stepladder, holding a 40-pound electric motor, trying to maneuver it into a housing unit. What is the hazard?
The primary hazard here is dynamic weight overloading. The math is simple addition, but the concept is structural integrity. You have 156 pounds of human mass, plus 15 pounds of dead tool weight, plus a 40-pound motor. That equals a total load of 211 pounds localized on a few square inches of aluminum or fiberglass step.
And as the safety professional, what are you looking for on the ladder itself?
You are looking for the manufacturer's duty rating sticker. Ladders are classified by the maximum weight they can safely hold. A Type 3 ladder, often called a household ladder, is only rated for 200 pounds. If that worker is using a Type 3 ladder, the system is overloaded by 11 pounds.
11 pounds doesn't sound like much. Will it really collapse?
It might not collapse while they are standing perfectly still, but remember they are maneuvering a heavy motor. When they shift their weight or push against the motor housing, they create a dynamic force that acts as a multiplier. That 211-pound static load suddenly exerts 300 pounds of force on the side rails, and the ladder buckles. You must ensure they are using at least a Type 2 commercial ladder, rated for 225 pounds, or ideally a Type I industrial ladder, rated for 250 pounds.
Beyond the weight rating, there are strict physical rules for how a human interacts with the ladder. Let's go over the mandatory do's and don'ts, starting with the golden rule.
The absolute golden rule of ladder safety is maintaining 3 points of contact at all times while ascending or descending.
Meaning 2 hands and 1 foot, or 2 feet and 1 hand are firmly on the ladder structure.
Exactly. It ensures that if one point slips, if your boot slips on a wet rung, you have 2 other points holding your center of gravity stable.
Which naturally brings up the concept of center of gravity and the belt buckle rule. Explain the physics behind this one.
A ladder is just a lever system balancing on a very narrow base. The center of gravity of the human body is roughly around the navel, or the belt buckle. The belt buckle rule states that you must keep your torso inside the vertical side rails of the ladder.
Because if you reach too far to the left to paint a corner,
you shift your body's center of mass outside the stable footprint of the ladder's legs. Once the center of gravity crosses that vertical plane, gravity pulls the top of the ladder sideways, pivoting on the opposite leg. The ladder tips over instantly. The rule is simple. Move the ladder, don't reach.
Another critical don't. Never stand on the top step or the top cap of a step ladder. You lose all knee support and your center of gravity gets way too high. But here is a contradiction from the manual that trips people up. It explicitly says, don't carry tools in your hands while climbing. But earlier in our scenario, the worker was holding a 40-pound motor. How are you supposed to get heavy tools up a ladder if you need your hands free to maintain 3 points of contact?
This is where we circle back to safety being a motivational problem. The textbook solution requires extra effort. The correct way is to wear a tool belt for small items. But for a heavy motor or a bucket of materials, the worker must climb the ladder empty-handed, establish 3 points of contact, get into a secure working position, and then use a hand line or rope to physically hoist the heavy object up to the work area.
But that takes 5 extra minutes. You have to find a rope, tie a knot, pull it up.
Exactly. It's tedious. It's much faster to just tuck the motor under one arm and climb one-handed. Workers take the shortcut because they are motivated by efficiency and speed. The safety professional's job is to motivate them to prioritize the slow, safe method over the fast, fatal one.
Okay, take a breath. We have spent an immense amount of time dissecting working at heights because falls are the leading cause of death in construction. But to pass the ASP exam, you can't just be a fall protection expert. You are expected to be a polymath. You have to understand toxicology, radiation, fire dynamics, and ergonomics.
The breadth of the exam is genuinely intimidating. It requires you to synthesize completely different scientific domains.
So we are going to initiate a massive, comprehensive review of the remaining scientific domains from the Bowen EHS materials. A masterclass in the mechanisms of safety. Let's start with Domain 1, Topic 9, Manual Lift Parameters. We are looking at the IOH lifting equation. What is the mechanism behind this math?
The National Institute for Occupational Safety and Health, NIH, created this equation to evaluate the biomechanical stress placed on the lower back during two-handed lifting tasks. Specifically, it analyzes the compressive forces acting on the L5-S1 intervertebral disc at the base of the spine.
The L5-S1, the exact spot everyone complains about when they say they threw their back out?
Exactly. The human spine is a terrible lever. When you bend over to pick up a box, your spine acts as the lever arm, the load is in your hands, and your lower back muscles have to pull incredibly hard in the opposite direction to keep you from falling over. The DAOS equation calculates a recommended weight limit in RWL based on a series of multipliers: horizontal distance, vertical height, frequency of lifting, and how good the grip is.
Let's talk about the ultimate exam hack for this equation. The materials call it spotting the zero. What does that mean?
It's a conceptual shortcut. The BCSP loves to test if you understand the anatomy before you punch numbers into a calculator. Let's look at the horizontal multiplier, the HM. This is driven by the horizontal distance h from the midpoint between your ankles to the center of the load you are holding.
How far away the box is from your stomach?
Right. The equation for HM is 10 divided by H. But OSHA establishes a strict biomechanical limit. The maximum allowable horizontal distance is 25 inches. At 25 inches, the lever arm is so long that the compressive force on the L5S1 disc is catastrophic, even for a very light weight. Therefore, if a test question states that the worker is reaching out 26 inches to grab a box,
If they are reaching past 25 inches, what happens to the math?
the task is considered automatically unsafe. Mathematically, the horizontal multiplier becomes exactly 0.
And since the entire recommended weight limit equation is just a series of multipliers multiplied by a load constant.
Anything multiplied by 0 is 0. If H is 26, the entire RWL is 0. You don't need a calculator. You don't need to look at the frequency or the vertical height. The answer is 0 pounds. The exam is checking if you recognize that reaching out past 2 feet is anatomically unacceptable.
That is a phenomenal conceptual shortcut. What if the distance is, say, 15 inches? The math won't be 0, but the resulting lifting index might show the task is hazardous. Using the hierarchy of controls, how do you fix a bad lifting setup?
Mathematically, the most impactful variable you can change is that horizontal distance. You engineer a way to bring the load closer to the worker's body. You remove physical barriers, use a turntable, or cut away the side of a bin. By reducing H, you increase the multiplier, significantly improving the safety of the lift. Also, for the exam, memorize the constants. The ideal load constant is 51 pounds, the ideal horizontal distance is 10 inches, and the ideal vertical height is 30 inches, which is roughly knuckle height.
Okay, shifting gears completely, let's dive into physics and mechanics. Here's a scenario you will see when analyzing vehicle accidents. A 4,000-pound forklift or automobile is traveling at 68 miles per hour. The driver slams on the brakes, the vehicle doesn't have anti-lock brakes, so the wheels lock, and the tires skid across the asphalt. The coefficient of kinetic friction between the rubber and the road is 0.8. How far does the vehicle skid before stopping?
This requires you to understand the work energy theorem. The vehicle possesses a massive amount of kinetic energy because it is moving. To stop the vehicle, the friction between the tires and the road has to do work to drain away all that kinetic energy, converting it into heat and sound.
I want to guess the mechanism here. If I have a 4,000-pound truck and an 8,000-pound truck going the exact same speed, my gut instinct says the 8,000-pound truck will skid twice as far because it has twice the momentum. Mass has to be a huge factor in the formula, right?
Your gut instinct is what the exam counts on to fail you. It is intuitively appealing, but mathematically incorrect. In this specific skid distance equation, mass actually cancels out entirely.
Wait, how does mass cancel out? A heavy truck has more energy.
It does. A heavier truck has more kinetic energy. But because it is heavier, it also pushes down on the asphalt with more force. The frictional force stopping the vehicle is proportional to the normal force, the weight pressing down. The increase in kinetic energy is exactly offset by the increase in stopping friction. Therefore, the mass variable appears on both sides of the algebraic equation and cancels out.
That is mind-blowing. So what does the distance actually depend on?
The skid distance is purely a function of the velocity squared, divided by 2 times the acceleration of gravity times the coefficient of friction. The critical takeaway is that speed kills, not mass, in a skid scenario. Because velocity is squared in the kinetic energy formula, doubling your speed quadruples your stopping distance.
Let's apply mechanics to lifting things instead of stopping them. Crane rigging. You are the safety professional overseeing a massive crane lift of a steel generator. You have a wire rope sling. What rigging configuration allows you to pick up the absolute maximum weight? Do you hang the sling straight down on a single leg? Do you wrap it in a choker hitch that tightens around the load? Or do you use a vertical basket hitch?
You must use a vertical basket hitch. Let's explain why by looking at how forces are distributed. A single leg hanging straight down supports 100% of the sling's rated capacity. It's a 1-to-1 ratio.
What about the choker hitch? You see that all the time, wrapping the rope around a pipe and hooking it back onto itself.
A choker hitch is great for holding loose bundles of pipe together, but it is terrible for capacity. By bending the wire rope sharply around the load and choking it back on itself, you create severe angled stress on the wire strands. That sharp bend crushes the internal core of the rope. A choker hitch significantly reduces the capacity of the sling, often dropping it to 75 or 80% of its single leg rating.
Okay, so choker makes it weaker? Why is the vertical basket hitch the strongest?
In a vertical basket hitch, you pass the sling completely under the load, and you attach both the eye ends of the sling vertically onto the crane hook. You've essentially created a U-shape. Because both legs of the U are pulling straight up, the weight of the load is distributed evenly between two parts of the wire rope. A vertical basket hitch effectively doubles the capacity of the single leg.
Simple geometry, but massive implications for not dropping a generator.
Okay, let's move indoors to Domain 3, industrial hygiene and the environment. We need to talk about ventilation. The text gives a complex scenario. You have a 10,000 cubic foot manufacturing room. There are two different chemical sources. One emits ethanol vapors, which has a permissible exposure limit, or TLV, of 1,000 parts per million. A second process emits nitrous oxide, which is much more toxic and has a strict TLV of only 50 parts per million. How do you approach this? You are dealing with dilution ventilation. You are trying to pump enough fresh air into the room to dilute the contaminants down to safe levels before the workers inhale them. To calculate the required airflow in cubic feet per minute, you must account for the generation rate of the chemicals, their specific gravity, and the target TLV.
But the air doesn't mix perfectly, right? If I pour cream into my coffee, it doesn't instantly turn light brown. It swirls around in clouds until I stir it.
That is an excellent analogy. In a room, perfect mixing is an illusion. Supply air often short circuits. It blows out of the supply vent and gets sucked straight into the exhaust vent a few feet away, leaving pockets of dead, stagnant air in the corners where the toxic nitrous oxide is building up. To account for this imperfect mixing, safety professionals apply a K factor, or mixing factor, usually between 1 and 10, to their equations as a massive safety buffer.
And how do you verify the exhaust is actually pulling enough air out? The text mentions velocity pressure. If you have a 15-inch circular exhaust duct and a pitot tube reading shows an average velocity pressure of 0.88 inches of water, what does that tell you?
Velocity pressure is the physical pressure exerted by the movement of the air. You use an equation that incorporates the density of air to convert that velocity pressure into the actual velocity of the air traveling down the duct in feet per minute. Once you know how fast the air is moving, you multiply it by the cross-sectional area of that 15-inch duct.
Area equals pi times radius squared.
Exactly. Velocity times area equals flow rate, or Q. If that final Q value isn't high enough to meet your dilution calculations, your workers are breathing nitrous oxide, and you need a bigger fan.
Speaking of respiratory perils, let's talk about particulates. We know silica dust from cutting concrete is incredibly dangerous. The exam will ask about particulate sizes. What size of dust particle is the most hazardous to human health? If I use my gut instinct again, I'd say the biggest chunks of dust cause the most physical damage to the lungs.
And again, your gut instinct would fail you. The most hazardous particulates are the microscopic ones, specifically respirable dust that is around 1 micron or less in aerodynamic diameter.
Why are the tiny ones more dangerous than the big ones?
It's entirely about how the human body's defense mechanisms are structured. The body is great at catching large particles. If you inhale a 100-micron piece of sawdust, it gets trapped by the hairs inside your nose, or it impacts the sticky mucus lining your throat and upper respiratory tract. The cilia tiny hair-like structures sweep that mucus upward, and you cough it out or swallow it. Large particles never reach the deep lungs.
So the body filters the big stuff out.
Yes. But a 1-micron particle of crystalline silica is so small and lightweight that it follows the airstream perfectly. It bypasses the nose hairs, it bypasses the mucus in the trachea, and it travels deep into the alveolar region of the lungs, the tiny air sacs where oxygen enters the blood.
And once it gets into those tiny air sacs,
there are no sweeping cilia down there. The body's last defense is to send specialized immune cells called alveolar macrophages to eat the silica particle. But silica is toxic to the cell. The macrophage eats the silica, dies, and ruptures, releasing enzymes that scar the delicate lung tissue. The body sends more macrophages, they die too, and the cycle of fibrosis begins. This is silicosis. It is incurable and caused entirely by invisible 1-micron dust.
That is incredibly bleak. While we are on the topic of invisible hazards, let's tackle radiation. The exam covers the differences between ionizing radiation types. What is the fundamental difference mechanically between alpha and beta radiation?
Ionizing radiation has enough energy to knock electrons out of atoms, which destroys human DNA. But the delivery mechanisms differ. Alpha radiation consists of large, heavy, highly energetic particles, essentially helium nuclei.
Heavy sounds bad.
It is bad, but because they are so large and carry a double positive charge, they interact violently with everything they touch, losing their energy almost immediately. You can stop a beam of alpha radiation with a simple sheet of paper or just the dead layer of skin cells on the outside of your body. Externally, alpha is barely a threat,
But internally?
If you inhale or swallow an alpha emitter-like radioactive dust, it is catastrophically dangerous. All of that massive energy is dumped directly into soft, living internal tissue, causing massive chromosomal damage. Beta radiation, on the other hand, consists of high-speed electrons. They are much smaller and carry a single negative charge.
So they penetrate deeper.
Yes. A piece of paper won't stop a beta particle. It will pass through the dead skin and burn the living tissue beneath. You need denser shielding, like a thick sheet of plastic, aluminum, or lead, to protect a worker from external beta radiation.
This leads to a fascinating trivia point from the exam prep that completely shocked me. If you survey 100 people living within a 5-mile radius of a modern nuclear power plant, what is the greatest source of ionizing radiation exposing that population? I assume everyone guesses the cooling towers or radioactive waste.
Yes, the public assumes the nuclear plant is blasting them with radiation. But the reality is that the greatest source of ionizing radiation for the general public, even living next door to a reactor, is naturally occurring radon gas.
Radon gas from the ground.
Yes. Uranium naturally exists in the Earth's crust. As it undergoes radioactive decay over billions of years, it eventually turns into radium, which decays into radon, an invisible, odorless, radioactive noble gas. It seeps up through the soil and gets trapped in people's basements. The regulatory controls on the emissions of a nuclear power plant are so incredibly strict that their contribution to public dose is virtually zero compared to the naturally occurring radioactive earth underneath their homes.
Which proves exactly why we need safety professionals running the numbers and analyzing data instead of letting public panic dictate policy. Okay, let's shift to fire and electrical safety. Imagine an office building. It is protected by a wet pipe fire sprinkler system. The sprinkler heads are designed with a thermal element that shatters and triggers the water when the ambient air reaches 100 degrees Fahrenheit. But the building is undergoing renovations, and the IT guys have removed dozens of the acoustic drop ceiling panels to run network cables. A fire starts in a cubicle. What physically happens?
The sprinkler system is going to fail to respond in time, and the fire will grow significantly larger than the system was designed to handle.
Why? Wouldn't the heat reach the sprinkler heads faster without the ceiling tiles in the way?
It comes down to thermal dynamics and convection currents. Sprinkler systems are highly engineered around the physical presence of a flat ceiling. When a fire starts, it generates a plume of hot gas. Heat rises. In a normal room, that hot plume rises, hits the flat acoustic ceiling, and banks horizontally, spreading out across the ceiling plane. This forces the hot air to pool directly around the thermal glass bulb of the sprinkler head hanging just below the ceiling.
So the ceiling traps the heat around the trigger?
Exactly. If you remove the ceiling tiles, you destroy the trap. The hot plume of gas rises, bypasses the sprinkler head entirely, and goes straight up into the open plenum space above the drop ceiling grid. The heat fills the upper void where the ductwork is, rather than pooling at the 100-degree trigger level. The fire in the cubicle grows massively, generating far more toxic smoke, before the ambient temperature near the sprinkler head finally reaches the threshold.
Wow. A missing ceiling tile seems like a cosmetic issue, but it fundamentally breaks the thermal engineering of the fire suppression system. Let's talk about extinguishing fires. If you are auditing a commercial restaurant kitchen with deep fryers, what class of fire extinguisher must legally be mounted on the wall?
A commercial kitchen requires a Class K fire extinguisher.
Why not just a standard red ABC dry chemical extinguisher? It puts out almost everything else.
A deep fryer fire involves hundreds of degrees of burning animal fat and vegetable oils. If you shoot a pressurized blast of standard dry chemical powder into a vat of burning oil, you're just going to splash burning grease all over the kitchen walls, and the chef instantly spreading the fire. A Class K extinguisher contains a specialized wet chemical agent.
How does the wet agent work differently?
It sprays out as a fine mist to avoid splashing the oil. When the chemical hits the burning fat, it triggers a chemical reaction called saponification. It literally turns the surface of the burning grease into a thick, soapy foam blanket. This foam smothers the fire by cutting off the oxygen, and the water content of the mist rapidly cools the oil below its auto-ignition temperature.
It turns the fire into soap. That is brilliant chemistry. And what about detecting a fire before it gets huge? Say you have a hidden void inside a wall where an old electrical wire is slowly overheating, melting its insulation, and creating a smoldering, invisible fire. Which type of smoke detector catches it first?
You want an ionization smoke detector for that specific scenario.
Not a photoelectric one.
No. A photoelectric detector relies on a beam of light. It waits for thick, visible smoke particles to enter the chamber and scatter the light beam onto a sensor. It is great for smoky, smoldering mattress fires, but an overheating wire might not produce thick, visible smoke immediately. An ionization detector uses a microscopic amount of radioactive americium-241 to ionize the air inside a chamber, creating a tiny electrical current.
Okay, so electricity is flowing through the air inside the detector.
Yes. When the microscopic invisible particles of combustion from that overheating wire enter the chamber, they attach to the ionized air molecules, slowing them down. This drops the electrical current and the alarm sounds. Ionization detectors catch fast-flaming invisible particulate fires much faster.
Sticking with electrical hazards, here is the classic office safety violation. A worker runs out of plugs under their desk. They take a power strip, plug it into the wall, and then plug a second power strip into the first one. They daisy chain them. They plug in a monitor, a laptop, and a phone charger. They're drawing barely any power. The power strips have internal breaker switches. Why does OSHA cite this as a violation?
OSHA citations for electrical issues often come down to the listing of the equipment. Daisy chaining violates the Underwriters Laboratories, or UL, listing of the device.
UL being the testing laboratory that certifies the equipment is safe.
Correct. When UL tests a relocatable TAPA power strip, they test it plugged directly into a permanent wall receptacle. They certify the thermal properties and resistance of that specific length of wire. When you plug a power strip into another power strip, you are adding resistance to the circuit. Exactly. More resistance means more voltage drop. And more importantly, it generates excessive heat inside the wires, denoted by the formula I²R. The internal breaker on the power strip is designed to trip based on current overload, not necessarily the thermal accumulation caused by daisy chaining. OSHA cites you because you are using the equipment in a manner outside of its designed and certified purpose.
Let's talk about ground fault circuit interrupters, the GFCIs. Those are the plugs with the little test and reset buttons. Where do we require those, and how do they actually work?
GFCIs are required in any potentially wet environment: bathrooms, kitchens, outdoor receptacles, rooftops, and temporary wiring on construction sites. They are designed to prevent fatal electrocution. Inside the GFCI is a tiny current transformer. It monitors the amount of electrical current flowing out on the hot wire and compares it to the current returning on the neutral wire.
What goes out must come back.
Precisely. If there is an imbalance of even 5 milliamps, meaning 5/1000ths of an amp is missing, the GFCI assumes that missing current is leaking out of the circuit. And if you're holding a wet power tool, that current is leaking through your heart and into the ground. The GFCI detects that 5 milliamp difference and physically trips the internal contacts, shutting off the power in a fraction of a second.
And how is that GFCI fundamentally different from the standard 20 amp circuit breaker sitting in the electrical panel in the basement?
This is a crucial distinction for the safety professional. They protect entirely different things. A GFCI trips at 5 milliamps to protect a human life. A standard circuit breaker in the basement is designed to allow 15 or 20 solid amps of current to flow continuously.
And what does 15 amps do to a human body?
It will stop your heart instantly and burn your tissues. The standard circuit breaker does not care if you are being electrocuted. It is not designed to protect human life. It is designed to protect the physical copper wires inside the walls of the building. If a short circuit draws 50 amps, the wires will overheat and start a structure fire. The breaker trips to stop the fire. Breakers protect property. GFCIs protect people.
Okay, we're entering the final stage of the gauntlet ergonomics, training, and statistics. If I am analyzing a workstation where an employee stands all day doing primarily upper body precision work like soldering circuit boards or assembling small parts, where should the physical bench height be relative to the worker?
Ergonomics is about minimizing musculoskeletal strain. For standing upper body work, the bench height should be positioned slightly below the worker's resting elbow height, usually by about 2 to 4 inches.
Why below the elbow? Why not right at chest level?
If the work is too high, the worker has to constantly shrug their shoulders upward to lift their forearms, which causes extreme fatigue and cramping in the trapezius muscles of the neck and back. By placing it slightly below the elbow, the worker can let their shoulders drop naturally, keeping their arms relaxed at their sides. It also allows them to lean forward slightly and use their core body weight to apply downward force if necessary, rather than relying solely on forearm strength.
And what are the primary risk factors for the musculoskeletal disorders that cost companies billions in workers' comp?
The materials highlight the big 3 ergonomic risk factors. First is frequency of motion performing the exact same wrist rotation thousands of times a shift without recovery time. Second is required force pinching, pulling, or pushing heavy loads. Third is awkward postures, working with the wrists bent or twisting the spine while lifting.
But the text notes a fascinating nuance about awkward posture. It isn't just about reaching too high.
Right. Awkward posture can be internally generated. A major factor is poorly fitting, personal protective equipment. If a worker is given a heavy protective suit that is sized too small, it restricts their natural range of motion. They're forced to contort their spine just to bend over. Or consider obesity. Excess body mass physically alters the biomechanics of how a person lifts and moves, inherently creating awkward postures that increase discompression. Ergonomics has to account for the actual bodies performing the work.
Which requires intensive training to help workers understand these risks. But as an ASP, how do you train them effectively? The text asks a great question based on adult learning theory. Which technique provides the absolute greatest participant retention? Is it reading the safety manual, watching an OSHA video, listening to a brilliant lecture from a safety pro, or actively participating in a role-playing training game?
Active participation provides the highest knowledge retention by a massive margin. Adult learning theory, or andragogy, emphasizes that adults learn best by doing. Reading a manual or listening to a lecture is a passive exercise. The brain doesn't have to engage critically.
You can stare at a safety video and mentally be at the grocery store.
Exactly. But if you put them in a tabletop game where they have to analyze a mock job site, identify the hazards, and defend their choice of fall protection to their peers, they're forced to synthesize the information. They make decisions, they get immediate feedback, and the lesson anchors deeply into their memory.
Which circles us beautifully back to the very first premise of our discussion. Safety management is a motivational problem. If you lecture an iron worker about physics, they fall asleep. If you engage them in a scenario that respects their intelligence, you motivate them to learn the standard.
Exactly. The human element is always the ultimate variable. And the final piece of the ASP puzzle is being able to mathematically prove to management that your training and your interventions are actually working. Which brings us to statistics.
Ah, yes. The math comes back for a final bow. We won't try to calculate standard deviations on air, but conceptually, the exam asks about data visualization. What is the fundamental purpose of a histogram?
A histogram is a graphical tool used to diagram the frequency distribution of continuous data. If you have a spreadsheet filled with 500 near-miss reports from the last 2 years, it is just a wall of meaningless numbers. A histogram organizes that data into visual columns, or bins.
So it tells a visual story.
Precisely. It instantly reveals the shape of the data. You might look at the histogram and clearly see a massive spike in near misses clustered around the third shift, or a sudden skew in hand injuries during the month of November. It takes raw, chaotic data and turns it into a recognizable pattern that the safety professional can use to target their interventions.
So after this incredible comprehensive review across domain 1, 2, and 3, what does this all mean for the listener? We've covered an immense amount of ground today on QHSE Talks. From the depths of the L5S1 spinal disc in an IO-H equation, to the dynamic shock loads of a 15-foot fall clearance, to the saponification of grease fires.
It means that passing the ASP exam, and more importantly, succeeding in your career as a safety professional, isn't about memorizing a list of OSHA rules in a vacuum. It is about internalizing a multidisciplinary philosophy of hazard recognition.
It's about seeing the matrix of the job site. When you walk into a warehouse, you shouldn't just see a forklift driving around. You should see the kinetic energy calculation and the friction coefficients of the tires. You shouldn't just see a missing drop ceiling panel. You should see the thermal convection currents bypassing the sprinkler heads.
Exactly. You are synthesizing physics, human biology, chemistry, and behavioral psychology into a cohesive, invisible shield that protects the workforce from their environment and from themselves.
And speaking of the future of that workforce and the environment they operate in, I want to leave you, the listener, with a final provocative thought to ponder. Earlier, we talked about elimination being the highest form of hazard control on the hierarchy. We talked about using drones for roof inspections or using robotics to handle radioactive materials. As we march toward the year 2035, automated technologies are going to increasingly eliminate the need for human beings to physically work at heights or handle hazardous waste or enter confined spaces directly.
Which raises a profound existential question for the industry. How will the definition of the safety professional evolve? Will the associate safety professional of 2035 be less concerned with the tensile strength of lanyards and the base plates of scaffolding and entirely focused on software reliability, algorithmic risk management, and the cognitive ergonomics of remote control interfaces?
If the Bowen EHS sources are correct, and safety is ultimately a motivational problem at its core, how do you motivate a workforce to stay vigilant when the hazards become entirely invisible? How do you foster a safety culture when the danger isn't staring a worker in the face from 50 feet up in the air, but is hidden inside thousands of lines of machine learning code that operates the robotic crane? Think about that as you crack open your study guides tonight. Keep your boots firmly on the ground and your eyes always on the hazards. Thank you for joining this in-depth session of QHSE Talks.